This is going to be our final step in finding our center, okay? And this will be one where what we're calculating the mass, the center mass of, is something that is not linear. So it's not going to be just a rod. It's not going to be a rectangle, which is just a fat rod. It's not going to be a triangle where you can tell what the area is just by looking, right? Because the area of a rectangle is just the base times the height. The area of a triangle is just half of the base times the height. What this particular shape will be is one that is a curve. And so you can't just eyeball or know what the area of something underneath that curve is. So you're going to have to take an integral to get the area of the whole thing, to get the a-hole. Once you get the a-hole, you can figure out the mass hole. That mass hole then is what goes into the equation that is 1 over capital M multiplied by the integral x dm to find your center. So this one is going to be, it's going to have an extra step. It's going to be 2 integrals done in order to find your center. But again, the thing to remember is if it's a curve, you're going to have to do some calculus to find what the mass hole is. Because it's literally just taking the area under a curve, which is the definition of an integral. So what I will use as an example again, what you've already done is calculate the area of this guy. You can tell it's just base times height and divide that by 2, right? That's easy, but this particular area, this particular shape is similar to a triangle, but darn it, it's got a curve instead of that straight line. So if it's a curve, then I can't say, well, heck, the area is just half of the base times the height, because it's not half of the base times the height, all right? When you have a curve like this, another thing you can't do is just say, well, gosh, y equals mx plus b, because it doesn't equal mx plus b. What they will have to do is give you an equation for what y equals. In this example, it's simply ax squared, some constant times the square of x. That will either be given, or they will tell you what all of these dots are so that you could then put them in your magic box, and your magic box could tell you what y equals in terms of x, since you all know how to do that, don't you? But remember, since this is an area, all right, our typical procedure is, let's start out with density. The density of this guy is a sigma, and that is equal to the mass of the whole object, the mass hole, divided by the a-hole, the area of the whole object. Since it's a uniform density, what we will say is that is exactly the same thing as if I were to slice it into differential masses and differential amounts of area. So a differential mass could be this thin little sliver of it right there, that dm. And if I add all of those differential masses up from 0 to L, I'll get the mass hole. It's the same thing if I add up all of those differential areas, if I call that a dA. If I add up all those thin little slivers area-wise, I will get the a-hole, right? So that's the procedure we'll use there. And again, the item is if I have a swap between a dm, which I will, that differential mass then is the same thing as the density times differential area. So it's a sigma times a dA. Remember, any given area is simply a base times a height, isn't it? A length times a width, whatever, a base times a height. So this differential area is going to be a base times a height. That base for our differential area is simply the thickness of this thin little sliver, which you should all know by now. We've done it several times. That's called a differential x. If I add up all of those dx's from 0 to L, so there's our base. The base in our differential area is a dx. The height then is however high up this thin little sliver goes. And that height is what changes, doesn't it? It climbs literally exponentially. So whatever that height is a function of the x, and that's what that equation tells you. Y is simply an h. It's how high up it is. So our height of this differential x is whatever y equals at that particular x, So the height is simply ax squared, all right? So there's our differential area, our thickness, which is the base, times however high up it is. So our differential mass is nothing more than sigma times ax squared times dx. So it is the density times the height times the base. That's our differential mass. Okay? Now, what I'll have us do is the same thing we've done before. I will calculate the x center mass of this object by taking 1 over the capital M, the mass whole, and I will multiply it by the integral from 0 to L of x dm. That equation, again, hasn't changed a bit. We just went through a lot of fuss to get what differential mass is. It is sigma ax squared dx. So what I will do is simply replace this with 1 over m times the integral from 0 to L x, where that dm is, again, it was a sigma ax squared dx. All right, so this guy is going to end up simplifying quite a bit because this sigma and a are constants, so I can fish out the sigma and the a. It'll become sigma a over the mass whole times the integral from 0 to L x to the third dx. That's it. You guys all know integrating x to the third, that's pretty easy. It's just x to the fourth over 4. So what I end up with is sigma a over the mass whole times x to the fourth over 4. And I go from 0 to L, which means all I have to do is plug the L right there, and we're essentially done. However, what ends up happening boom, huh? Remember what we've done before. What we did before is we had this m replaced in terms of a density, so I can cancel out that sigma. So if I want to replace that mass in terms of a density, then this is what I was saying at the beginning. We're going to have to do another integral to get what the mass whole is, because this m is the mass of this whole object here. And we go back to this formula where the density is the mass whole divided by the a whole, isn't it? Which means the mass whole is equal to the sigma times the area, isn't it? Right? So what I'm going to end up doing is calculating what the mass, capital M, is, and it is equal to sigma times the a whole. Well, the area of the whole thing, I have no idea what it is. It's the area underneath the curve, but it's probably going to be the sum of all those differential areas, isn't it? The a-hole is the sum of all the tiny little a's. And so this, again, is just an integral. If I want to know what the area of the whole thing, the area under the curve is, I need to add up all those differential areas. So what that differential area is, the mass equals the density times the integral of the differential areas from 0 to L. What is a differential area? All right, so what I will do is come back up to what we did earlier. I had a differential area written right there as simply a base times a height. The height is ax squared, the base is dx. So what I will do now is have a swappertuna dA based on what we said earlier the differential area is. So this becomes the mass of the whole thing is equal to the density times the integral from 0 to L, where that dA is, I'm going to replace it with ax squared dx. So all I'm doing is integrating ax squared and multiplying it by the density. That's it. So a is constant, isn't it? This will be sigma a x to the third over 3. All right. All I did was fish the a out and then integrate x squared. It's x to the third over 3. I'll go from 0 to L, and it becomes sigma a L to the third over 3. That is what capital M equals. That's the mass hole. All right? So do you see now this circled M is that circled M. So what I'm going to do is put all of this where that M is. All right, so it will end up looking like this. Sigma is that sigma. A L to the fourth divided by, now where this M is where that M is, which is sigma A L to the third over 3, and then I multiply that by this 4 right there. Okay? So again, all I did was put this mass where that mass is to make it look like this. So now to clean this up a bit, you guys all know that those sigmas die, those A's die. This L to the third kills all of those except one L. And what I'm left with is L over 4 over 3, which you guys all know is, whoops, I almost said 4/3. It's 3/4 L. And that's it. That's the X center mass of this particular object, 3/4 of the length. So this guy over here, its X center mass is 3/4 of the way over. It's much heavier on the right than it is on the left, heavier than even just a regular old triangle like we integrated before. And again, the reason why we had to do 2 integrals this time, we did 2 integrals, right? We did one, our normal integral to find our center. The reason we had to do a second integral was because to find our mass hole, we needed to find the A hole. The area under a curve required an integral in this case because the curve is just that, a curve. So if you have to do calculus to find an area under a curve, then you have to do calculus to find an area under the curve. It's really that simple. So the reason we had to do 2 integrals that time, because it is a shape that you can't tell the area just by looking. So it's a definition of an integral, kids, figuring out what the area underneath the curve is. So once you do that, it's easy. And some students like to find the mass hole before they find the center mass. You could do it in either order. Some students say, oh, that's a curve. All right, I'm going to find the mass hole first by doing what I showed you off to the side there to do it before you start the center mass calculation. But doesn't matter. But hey, that's why we had to do that. So we are done giving straightforward examples of finding your center. Now the rest will just be more practice problems that I'll give you, and you'll get pretty darn good at finding your center. Yay, physics.